Hey, how's it going, everyone? So this is the last video of exponents when it comes to equations and things like that. So it won't be such a long video, but I want to make sure I go through every possible scenario that you're going to see. So I have one, two, three, four, five, six, about 7 questions to go through. Okay, so let's just review as we usually do what we're up to and what you've learned so far. So in this Unit 9, we have established some rules of exponents, which are important, how to go from radicals to exponents and vice versa, knowing that, something with a fraction as an exponent is really not a big deal anymore. There's so much we can do with it. Okay, how to simplify expressions with different exponents into a single radical. That was kind of cool. Now we know how to solve this, right? We would raise everything to the reciprocal. And we just learned how to solve this, which is squaring both sides. Okay, so today we will learn how to solve this, which is a little nutty. You've got 3 to the 2x, and it's equal to 27 to the x plus 4. So where do you begin? Okay, well, I can't use the reciprocal business, because I don't even know what that would be. I guess 1 over 2x, 1 over 2x. Well, that won't help. So let me show you something. The idea today is called common bases. Common bases. And how we're going to get those is by finding out what we can do with expressions, how we can make them look different. For example, the number 8. Not too hard to imagine that. That can be written as 7 plus 1, 4 plus 4, 6 plus 2. It's a million combinations. In fact, it's limitless. How about 30? If we were using multiplication, 15 times 2, 10 times 3, and so on. So in the exponent world, where we are now, when we want to make things look a little different but maintain their same value, this is what we do. We take a 64 and say, oh, I got you. You're 8 squared, right? That brings us into the exponent world. 27 is 3 to the 3rd power, believe it or not. 3 times 3 times 3. It's 27. Now the cool one, which to be successful in this unit you're going to have to recognize and remember, is when you get something like this, 1 over 8, it's not exactly obvious. How would you make that in exponent world? How could you rewrite it? So my tip to you is if you ever see fractions, just think of those negative exponents, because after all, how would I get an 8 to be on the bottom of any fraction? I would make it a negative exponent, which would then send it downtown as a positive exponent, right? So if we look at 1 over 8, oops, sorry, my bad. Okay, if we look at 1 over 8, we can write that as 2, not to the 3rd, but to the negative 3rd. Because after all, that would be equal to 1 over 2 to the positive 3rd, and there's what you were looking for. So this will be the gotcha, and this will be what you want to remember. Anytime you see fractions, just think negative, and you'll be fine. Okay, so here are the steps we're going to use to solve these 2 examples, and then about 5 more that have, unique features with them. So number 1, if there's any combining to be done, we do that, because what's really important is we want it to look like this. We want it to be expression equals expression. Then we're going to try to find something in common called the common base. Step 3, we will now rewrite these in the same base, but we won't disregard the original exponent. We'll keep that on the outside of the parentheses, and then we'll use the power rule and then solve for x. Whoa, sorry. That's better. Power rule, solve for x. So what are we talking about? Okay, take a look at this equation here. 5 and 25 are the bases. Well, using exponents, what can I make these two look like so that they look the same? I'm thinking, because it's pretty obvious, right? With a 5 and a 25, I can keep the 5 the way it is, like maybe just say 5 to the first, that's fine, and keep the exponent on the outside. I really didn't do anything to that guy. But it's this other one over here, which I'm thinking I can make look like 5 squared, because after all, that's 25. And I'll keep the original exponent outside the parentheses, because I don't want to change that. So what did I do? I took the 5 on the left, kept it a 5. I took the 25 on the right, I kept it 25, but I wrote it as 5 squared. And here's what that does for us. It's already starting to show us that we have these common bases. Both sides of my equation both have 5 now, right? So let's use the power rule, and I would get 5 to the very obvious 3x minus 8, and that's equal to 5. Distributing here, I'd get 4x. Here's the thing. When you have an equation of two expressions, one expression equals another expression, if those bases are the same, they're as good as gone. And we just solve for the top, and it is that easy. I mean, look at this equation, right? 3x minus 8 equals 4x. Who can't solve that? Watch, I can't. Let's see. No, I can't. Okay, I'm going to take away 3x from both sides. And that leaves me with an x over here and a negative 8 over there. Gorgeous. Pretty cool, right? So it's all about this. Whatever numbers you're dealing with, you're going to have to kind of figure out what they can be written as so that the base number is the same. And some of these might not be so easy. You might have to go through your calculator. But after a while, you'll get used to knowing and recognizing which numbers have certain bases. You know, like, oh, that's a 3, or oh, that's a 4. It'll come to you just with practice. Okay, this example on the right, 32 and 8. I like this example because you're going to have to change both of them. Using exponents, I can't make any of these an 8 or a 32. I'm going to have to pick a different number. So I think it's 2. Yeah, between an 8 and a 32. I know I can make a 32 2 to the something. 2 to the second is 4, to the third is 8, to the fourth 16, to the fifth, okay, to the fifth is 32. And then the number 8 I can write as 2 to the third. So there it is. I've got this common base of 2. So let me go back and plug it into the original equation. For 32, I'm going to say 2 to the fifth and be very careful with parentheses. I want to keep my original exponent like that. Okay, then I'll put 2 to the third over here and keep the 3x attached. Now, you do the power rule, which lets us write this. 2 to the negative 10x minus 15 is equal to 2 to the 9x. And there it is. Common bases of 2. So it's as good as getting rid of them and just solving for the top, the exponents. Negative 10x minus 15 equals, I hate when that happens. Hang on. Okay. Where was I? Oh, red. Negative 10x minus 15 equals 9x. Cool. So let's solve. I like to keep my x's positive, so I'm going to add 10 on both sides. You can go either way. So that gives me negative 15 equals, wow, 19 x's. Okay. Divide both sides by 19, and x equals negative 15 over 19. Not bad. Okay, so let's recap. Exponential equations, right? Equal signs and exponents. That's a fancy way to say exponential equations. How do you solve them? Well, If you can't use the reciprocal business, where you take your fraction exponents and raise them to the reciprocal, then why don't you look to make the basis the same? And once you do that, you cross out the bases and just solve the exponents as if they were their own equation. Let's try some more. Now the next ones I'm going to do are each different. So stay tuned and look at each one because it shows a little bit of a different look that you might see in the class or on your regents or any exams we have. These are all the different concepts. So what's a concept here? I see fractions. I'm thinking negative, right? So my numbers are 9 and 27. The only thing that comes to mind would be 3 squared. And if I can do 3 for 27, I'm in luck. And you can. 3 to the third is 27. So those will be my numbers. It'll be a base 3 and a 2 and a 3 exponent. Now, how do you do the fraction? Well, you know that now. Now you know it's going to be 3 to the negative 3. Put that in parentheses just for good habit, even though you don't need it here, because there was no original exponent attached. On the right-hand side, I'm going to write 3 squared instead of 9, and raise that to the original x minus 6. Let's use the power rule. That's what you get. Cross out the bases because they're now identical. And we have this fairly simple equation to solve. I'm going to add 12. Okay, 2x is equal to 9. Divide by 2. X equals 9 halves. And there you go. Okay, the idea with this question. It's not exactly that easy or straightforward because it's not an expression equals an expression. It's like 2 expressions equal an expression. So we want to do everything we can to combine them into one. Now, do you notice? These are like terms. This is 64 to the first and 64 to the n plus 1, negative n plus 1. Well, what's the rule of multiplication of the same bases? We can add those. So on the left, I can make it 1 by doing this. Okay? So what does that turn out to be? This is going to be 64 to the 2 minus n. And that's equal to 1/8 to the negative 2n minus 3. So now we have expression equals expression. Perfect. Let's get the common base. I have 8 and 64. So I think it'll be 8, like that. That's my common base. Okay, let's rewrite this. 64 is now 8 squared. And 1 over 8, there's that weird thing again, right? Fractions. So negative exponent. So I'm going to make it negative 1. So 8 to the negative 1. And let's raise that to the negative 2n minus 3. Okay, I've got the same bases, so they're gone. Let's use the power rule to get 4 minus 2n on the left side and positive 2n, positive 3 on the right. And look at that easy equation. Let's just solve for n. I'll add 2n to both sides. Again, I like to keep them positive. 4 equals 4n plus 3. Let's take away 3 from both sides. I'm running out of room. Hang on a second. Sorry about that. There we go. 4n is equal to 1. Divide by 4. Oops. Wrong way. Sorry. That's funny. I didn't mean to cross out the n. N equals 1/4. Look at that. Really cool. Okay, so let's go back to the top. What was the thing here? Yeah, expression equals expression. So make sure you have to combine your terms, whether they're on the left, the right, or both, so that it's expression equals expression. Okay, this is just a cool example in terms of the answer. It's going to be kind of neat. So 9 to the r is equal to 1 over 3 to the negative 2r, or something like that, right? So I hope you're getting used to this now where you're saying, oh, this is easy. I know my common base is going to be 3, right? 3 will be 3 to the 1. 9 could be 3 squared. So there's a fancy schmancy fraction over here, which is 1/3. So I'm going to call that 3 to the negative 1. Okay, so let's rewrite. I'm going to use 3 squared, raise that to the r, and I'm going to set that equal to 3 to the negative 1, raise that to the negative 2r. Bases are the same, sayonara to you. Let's use the power rule. And look at that. 2r equals 2r. Well, of course it equals 2r. What does that mean in terms of an answer? So I tried to give you a hint in the little title. It's everybody. R could be a million and these two would be the same. R could be negative a million, these two could be the same. You know what I mean? So the answer is R is like all real numbers. And when you're at those dinner parties that we always talk about with all the math teachers, they'll probably like to say this. R is equal to double R. That means like all reals, you know? Or you can get really fancy and say like R is an element of the reals. Anyway, the bottom line is it's everyone. All real numbers work for this original equation. Now, this is juicy. If anyone has Misatori, you know what I'm saying. This one is juicy. Okay. Why'd I throw this in? Okay, I threw this in because, you know, it sort of is expression equals expression, but we've got to simplify this expression first, you know. So 216 is the base on both of these. So we're going to subtract because that's the division rule, right? So let me simplify that fraction first. 216 to the negative 3p subtract negative 3p minus 1. Oh man, those parentheses are so important, especially with these double negatives. 36 to the 3p minus 3. Okay, what are we looking at? Negative 3p subtract a negative 3p. Well, that's over. They're gone. Now this is the key right here. Don't forget this negative to that negative. So I'm going to have 216 to the positive 1, which I don't really have to write, but I want to show you. That's equal to 36 to the 3p minus 3. Now, not so easy to see, but what do you think a common base is between 216 and 36? I'm going to start with the 36 and figure it's probably 6, you know? This guy is 6 squared. So 6 squared is 36. If I do another 6, that's 36 times another 6. 180 plus 30. Yeah, there it is. 216. That's literally how I figure this out. I mean, I've done these for a while, so some of them are easy for me, but you basically just use your calculator. There's no like surefire method for this. It's not like we're not showing you the trick. It's just you got to figure it out on your own, and that's what I do. So this is going to be 6 to the third, like that. Okay, so let's rewrite this. 6 to the third to the first, right? That's the original exponent. Just for good habit, I know that's useless, but just for good habit, is equal to 6 squared with the original guy outside. Cool. Check it out. Common basis. Beautiful. Let's use the power rule, and this is what we should get. 3 is equal to 6p minus 6. Solving for p, looks like I have to add 6. You're gone. 6p is equal to 9. divide by 6. P is equal to, what does that look like? 2, 3 halves. Perfect. Awesome. And is there one more? Yeah. Okay. Check out this one. This is just another case you might run into, right? There's no helping this one. It's a lost cause. Okay. Remember, expression equals expression, so let's combine these. So you've got 36 to the negative 2b plus 2b minus 2. That's equal to 216. Okay, adding exponents, I get negative 2b plus 2b. Oh, okay, those are gone. I'm left with a negative 2 is equal to 216. Common base, I think you remember from the last problem, is 6. Okay, so 6 squared with a negative 2 on the outside equals 6 cubed with really just a 1 on the outside, right? Common bases, goodbye. 2 times negative 2 is negative 4. 3 times 1 is 3. That's the problem. This is no good. How in the world could negative 4 be equal to 3? So that just tells you that this original equation, this guy, is unsolvable. There are no solutions. So that's it. And how do you do the dinner party situation with no solutions? You do one of those squiggly brackets. You put a little circle with a line through it. Or if you're good with your words, use your words. You just do this. No solution. Okay? So I think I've shown you everything. Yeah, I've got the no solution question here. A juicy one, which I kind of like. And all answers, right? You might fall into that one day where everything works. This guy with combining, you know, how you have to have expression equals expression. And then what do you do when there's fractions? Just always think negative. So I hope you enjoyed the lesson. I tried to keep it kind of brief, and you'll have plenty of time to practice in class. I wish you luck, and have a good night.